Okay, we have how is Ka calculated. Now, we have a bunch of different types of K, which is pretty much in reference to the solubility of that molecule. We have things like KSP and Ka. I think those are the only two that I can think of off the top of my head. And so KSP is usually dealing with solubility for like insoluble materials, pretty typically. So like when you have things like calcium oxide or something that's being formed, I think that's insoluble. But yeah, those things have certain KSPs. They have to calculate based on how much of it would actually still dissociate. Because even if it's insoluble, you will find that there's still a little bit of dissociation that occurs in that solid. But when they ask for Ka specifically, this is the dissociation constant for acids specifically, okay? Because we also have Kb as well. Thank you, I just remember another one, which is just the dissociation constant for bases. So Ka is asking how much of this acid would separate into its conjugate base and H3O plus. So really, the formula we have here, and it's important to write this formula like this because it helps us set up how Ka is calculated. So we have Ha, aqueous, and that's going to be important, as you will see. H2O, liquid, dissociates to A minus, which is a conjugate base, plus H3O plus. Okay? So with this being said, okay, the key thing here is that Ka is calculated as products over reactants, right? But the products and reactions you don't add in are typically things like solids, liquids. You usually typically either are working with gas. This is not just for Ka, but like for K in general, when you find dissociation, like with gases and everything else, you would put gases there. But exactly, you don't put things like solids or liquids. And you'd also work with aqueous solutions. Reason why I mentioned this here, because in this aqueous solution, think of water like just what it's in a sense surrounded by. Although it's reacting in this equation, it doesn't really take part in calculating the Ka, just because in a sense there's so much of excess of it because we're in a water system. So with that being said, we don't count water, so I'm going to pseudo cross it out. So as I said, products over reactants, we have Ka is equal to multiplication of products as A minus concentration and H3O plus concentration divided by HA. Okay, so this right here would be how you calculate Ka. Now in regards to how you actually go about it, typically you would use ICE tables, so initial change, equilibrium. A question would give you like a certain amount of HA, the concentration, so you know that HA, A minus, and H3O plus, you give a certain amount, so it'd be like let's say it was Q, okay, and they would say yes, you're given this amount and it's dissolved. Well, I mean, it's not dissolved in the solution, but how much acid is produced when this HA dissolves in water. So you have that Q there, and because you haven't it hasn't dissolved anything yet, these usually typically start at 0, unless the question says we already have this much acid there, like H3O specifically. Typically everything else is 0, and then as you can see in this formula, for every X amount you lose, you gain 1 X amount for each. So you have Q minus X, and then you have X and X. And then as your, well, plus X is a change, and then you have X and X, and this will end up with Q minus X as the equilibrium. So considering that A minus and H3O both start at 0, typically you'd have both of them X's, so you usually would put, to find the Ka, it'd be X squared over Q minus X. Now, after this, it depends. You can either use a quadratic equation, or you can simplify this further based on the fact, like, just as how there's insoluble materials that still dissolve just a little bit, they're quite weak acids that dissociate and ionize, but the things that the amount that produces is so little and so insignificant that you pretty much still have just Q. So you can either use your quadratic equation to solve for that by rearranging, or you can just say x squared over Q, and then you just find the square root of Q times the Ka, and both of them would help you. Sorry, all the time solving for x, but this would be how you go about solving for x, which would be your H3O based on a given Ka. If you weren't given a Ka, okay, and the question said this much was produced, like this much of conjugate base and acid was produced from HA, the way you would then solve that is that you'd want to make sure that you have your amounts of conjugate base in H3O, and whatever starting amount they gave you for the HA, you want to subtract one of them, because as we said, every x is produced when minus x subtracted. So if I said what is a Ka if 0.001 is made 0.001 of A minus and H3O is made from 1 mole of HA. So in reality, instead of it being just 1 mole, it'd be 1 mole minus the 0.001, which is quite small, but you still want to factor that in to really get that Ka value. And so we go ahead and say, based on this formula, we still have x squared over Q minus x. So we have x squared, which is 0.001, so we square that, divided by 1 minus 0.001, and then we know now that our Ka value would be 1, 2, 3, 4, 5, 6. It'd be 1.001 times 10 to the negative 6 in this theoretical case, which makes sense because that would show that this is indeed a pretty weak acid. So that would be how you do it. Exactly, like these still are your best friends just because you can still understand them. I wouldn't use this one then, just because we are finding Ka and not the actual x value. We don't need to use any quadratic formula. So with that being said, this right here will be how you calculate your Ka, and you're good to go. So as they said, it is products over reactants. They have CD over AB. They're thinking more exactly like K equilibrium, which is a general term for just the dissociation at equilibrium. But for Ka specifically, we're referring to a dissociation of an acid. So this is still correct because at least it has the basic down of products and reactants, but Ka works just slightly different than just finding the Keq.